So this is, surprisingly for me, my first time to Chicago. Whoever put my name up on the marquee at Chicago Theater, thank you. That was really awesome. My name's Casey. I'm an engineering manager for the chaos team and the traffic team at Netflix. And so I'm going to tell you a little bit about what those teams do, a little bit about chaos engineering and intuition engineering, and how they help keep the service at Netflix always on. Those of you who aren't familiar, Netflix is kind of like Blockbuster, but online. Another way to think about it. That's okay. I'll just hit the keys. Yeah. Blockbuster who? Another way to think of it is it's kind of like Facebook, but instead of people for friends, your friends are movies and shows that you've watched. With the advantage that on Netflix, they're not going to disagree with your political opinions. And like Facebook, Netflix is pretty popular. We're worldwide now, except for in China. And thankfully for us, people like us. So when our service is down, a great sadness falls on the internet. And I don't want to dwell on that again too much. Again, this is the always on track, so we're going to talk about how we keep the system always on. So at Netflix, again, we're large. Like Facebook, we're a lot of people use us. We're very large. We stream somewhere around the order of 4 billion hours of videos per month, which is a lot of data. Turns out that's about 40% of the internet at peak is Netflix traffic. And of course, most of that is served out of a CDN. Now, cache expiry, distributed caches, that's a solved problem in computer science, right? So that's boring. So we're going to completely ignore the CDN. I'm sure you don't have any questions about that. And instead focus on the other component to the service, the control plane. So the control plane, when you're using Netflix, everything from signing up to logging in to choosing a movie, negotiating DRM, all the way up until the movie actually starts streaming to your device is all handled by the control plane. Turns out that's fairly large as well, and we deploy that entirely in the cloud, in Amazon specifically, AWS. So the control plane is deployed in 3 regions in AWS. If you're not familiar with AWS terminology, you can kind of think of a region as a data center, although it's not actually that under the hood. And that's the world that my team lives in, working with the control plane. Now, when I look at an architecture or when I look at an engineering team, one of the ways that I measure the architecture or the team's sophistication is how well they optimize for these 3 things. So in my experience, a young company or a new product will often try to optimize for one of these things at the expense of the other 2. So we have performance, fault tolerance, and availability. And a team with more experience, again, in my experience, tends to be able to balance these 3 things better. And Netflix adds a 4th thing to this triangle, which is feature velocity. So at Netflix, we put a high priority on feature velocity. We believe that one of our critical competitive advantages is the rate at which we introduce new features. And we have a very sophisticated A/B testing system that gives us data to back this up. So to get feature velocity, one of the architectural choices that we made a while back is to move to a microservice architecture. Now, a lot of you probably have experience with microservice architectures, and your microservice architectures, there's a lot of different varieties. So I'm going to describe what I mean by microservice architecture so that you know where I'm coming from. So here's a very simplified example with just 7 services represented. And a service might be as simple as handling just login. Another service might handle just subscriber data. Another service might handle movie data, that sort of thing. And the way Netflix is structured, we have many small engineering teams that are responsible for one or more microservices. So the subscriber microservice is fairly large. That's a critical component of the service that we offer. So we have just a small team of 4 to 5 engineers who just support that microservice. So when somebody uses Netflix, either from a smart TV, Xbox, website, smartphone, what have you, a request comes in, and we'll just give a hypothetical example here. Request comes into Service D. We can imagine Service D as a proxy or API layer or something like that. And whatever that request is, that service isn't going to have all of the information that it needs to return the response. So Service D is going to reach out to Service C and Service F. Service C might be the subscriber data. Service F might be movie data. And those will in turn will reach out to A, and F will reach out to B and G, and A will reach out to B, and G will reach out to B as well, and also to E. And you can see that this quickly gets pretty complicated. If any of you saw Katie's presentation yesterday in the distributed systems track, she put up the Death Star view of services, and it gets pretty complicated. Netflix has somewhere around 400 services, microservices, in our system. Not all of them are in the critical path. Not all of them are in the streaming path. But again, this example of just 7 illustrates the point that the communication between those microservices can get pretty tricky pretty quickly. And then once they have the information that they need from downstream services, they bundle it up, they wrap up their request and send it upstream, and eventually that response is returned to the device that accessed the service. So I want to talk about a specific property of distributed systems like this one, like this microservice system. And to do that, I'm going to need some beer. I'm going to tell you a story. Take a little diversion with me into systems thinking. Now, if you take a systems thinking class in university or an MBA program, you'll probably at some point play the beer game. And the beer game is unlike any beer game that I played in college. So bear with me. I'm going to describe the rules to a simplified version of the beer game, and then I'm going to take us through an example round of the beer game. So in the beer game, there's 3 players, or in the simplified version, there's 3 players. They're customers who like to drink beer, retailers who sell beer, and manufacturers who make the beer. And if we were actually going to play this, what we would do is we would separate the class, the room, into 3 groups. Each group represents one of these one of these players. And they're not allowed to communicate with each other except by passing slips of paper back and forth, messages, with intent to acquire or exchange of beer or cash. So they're really not allowed to communicate with each other. And I'm going to throw some numbers up on the screen now. You don't have to follow the numbers along, just follow my narrative of what happens. So in the first week, we'll call this week 0 of the beer game, demand for, but we're engineers, so we'll call this foo beer. And I'm going to turn Wi-Fi off so that doesn't happen again. So we'll call this foo beer. So demand at week 0 is for 1 case of foo beer. And so a customer goes in, buys 1, the retailer has 2 in stock, so after that purchase they have 1 remaining. They order 1 from the manufacturer, has 8 in stock, and the manufacturer is bottling 1 case of foo beer. So we've got 1 at either end of this system, so we're in equilibrium. And then as the game really starts, in the first week, the antagonist in our story, we'll call him Nathan. Nathan wants to get drunk. So he goes to the store, and he's a desire for an additional 3 cases of foo beer. But he can only buy 2 because the retailer only has 2. So I indicate that with a -2 in the remaining column as like a dissatisfied back order. And the retailer wants to, get ahead of this, so they order 4 from the manufacturer, and the manufacturer sees this increase, and they start bottling 5 cases. And Nathan gets really drunk and comes up with this brilliant algorithm. Okay, he's pulling from quantum co-location and nanotech, and he's running it through a Lorentz transformation in relativistic physics, and he figures out a way to beat CAP theorem. And he publishes a blog, and it makes it to Hacker News, and because he was inspired by foo beer, he names it the foo beer algorithm, FBA, of course. And so there's a rush on foo beer. So demand spikes to 64 cases, but people can only purchase 8 because the retailer only had 8, so there's a loss there of 56 sales. The retailer sees this spike and wants to stay ahead of it, so orders 70 from the manufacturer. The manufacturer has the option to build a new distillery and bottle 250 cases at a time, so they go ahead and do that. But the protagonist of our story, we'll call him Steve, is a beer aficionado, so he gets one of these last bottles that's floating around, takes one sip, spits it out, says, that tastes terrible, sits down and writes a blog post proving that Nathan was full of beer, and that CAP theorem is in fact safe, and the algorithm was crap. So the next week, we're back to just Nathan, who wants to buy more cases of foo beer to drown his sorrows in. At this point, the manufacturer delivers their 250 cases, and finally we get back to steady state, where our demand is about 1 case per week, but we end up with this really disturbing result. So now the point of the game for the teams was to maximize value, and value for the customer was customer satisfaction, for the retailer it was sales, for the manufacturer it was also sales. And had we played a longer round, when you play this, usually the rounds are a lot longer. Usually there's more steps in the distribution chain. And usually you end up with this exact result, which is not these particular numbers, but which is really frustrating in that the retailer ends up with 76 cases that they're not going to be able to sell now. They missed out on selling 58 cases, so that was lost profit. The manufacturer has 180 cases they're never going to get rid of, and an extra distillery. WTF are they going to do with that? It's generally a frustrating experience for people who play, and I don't want to leave you frustrated, so here's a piglet eating ice cream. So why do they teach this in systems thinking classes? Well, specifically, I don't think it's because the professors have a superiority complex. That never happens. I think it's to demonstrate a specific systemic behavior called the Bullwhip Pattern, where a small oscillation in input in the system produces a much bigger oscillation further down in the system. I think there's a more important point here, which is that the customers, the retailer, and the manufacturer, none of them did anything wrong. They all made correct decisions given the information that they had and the scope of what they were responsible for. And yet the systemic behavior was highly undesirable. And there's a direct analogy to distributed systems like microservice architectures here. For any given services, for these services, say the subscriber service, that could be formally verified, perfectly to spec, absolutely correct. And yet, even if all of those microservices are absolutely correct, the system as a whole could still exhibit behavior that's highly undesirable. I'll give you another hypothetical example. So here's another story. Not that this has ever happened to me, but say you're in Washington, D.C., and you're on the Amtrak going back to Philadelphia because you lived there at the time. And you think, oh, it'd be great. It's nighttime on the Amtrak. It's late. It'd be great to catch up on House of Cards. And you're so engrossed in House of Cards that you drool on the keyboard, right? Like, this is embarrassing, but it could happen. And it's dark and it's late, and so you start fumbling with the laptop, and I have no idea what you hit, but your laptop starts just refreshing Netflix, which is weird, but okay. On the Netflix side, you're on a train, so the requests were, there was a network partition, and then they were buffered, and then they all hit the server at once. And because the requests are very similar, you're the same user, all those requests go to the same server for the subscriber service. It's trying to look up your information over and over again. And because it gets all these requests at once, it doesn't have time to look them up to look the data up off disk. So it has a very sensible fallback. It serves responses out of cache. They're not quite as up to date as what's on disk, but it's still an acceptable fallback, right? We don't want the service to shut down when a server gets overloaded. We just, so the way this manifests is if I went to the home page, I might see instead of movies that were personalized for me, I might see just like the top movies for everybody or something like that. So that's reasonable. So this one server in the cluster is serving from cache, and because it's serving from cache, its CPU load goes down. And say we have another service that's responsible for auto-scaling, because we don't want to pay for servers running when we don't need them. And it notices that the average CPU load goes down for the subscriber service. So it says, oh, okay, well, we don't need as many servers there then. And it kills one of the servers that has higher CPU load, which further lowers the average CPU load. And now the servers in the subscriber service are handling more requests with less machines to do the work. So more of them start flipping into cache. And the CPU load goes down further, and so the autoscaler shrinks the cluster further. And now many users, more than the one who just rolled on his keyboard, because he's a dope, start looking at Netflix and noticing, hey, this isn't what I usually see. And a very reasonable thing to do if you're a human and a program isn't working quite the way you want it to do is you start unplugging it and replugging it in or clicking refresh really quick. And all of a sudden we have a human created retry storm hitting Netflix with all of these requests, most of which will never complete, because by the time they even could get all of the context to return back to the user's already initiated a new request anyway, so it's essentially wasted work. I have no evidence that what I actually just described has happened at Netflix, but similar things have happened, and it's certainly the kind of systemic behavior that can happen in a microservice architecture or in a distributed system that we want to address. So far we've been drowning and I'm just describing the water, right? I've just illustrated the problem. I haven't given you a solution to anything yet. So let me tell you another story. This one about chaos, a happy story. At Netflix, we have two primary chaos tools, Chaos Monkey and Chaos Kong. And I'll briefly describe each. You might have heard of Chaos Monkey. This is a program that will, for a given service, randomly choose a server and turn it off during business hours. The reason that we built this is because we were tired of being paged at 3 a.m. in the morning, the witching hour, when servers usually disappear. So instead, we brought that pain forward during business hours so that when we got paged, it didn't matter as much. Now, at our scale, at anybody's reasonable scale, it's guaranteed that servers are just going to disappear because hard disk goes bad, somebody trips over a cable, power goes out, somebody shoots at fiber optic connectivity lines in the Midwest, true story. All sorts of backhoes, all sorts of things happen. So servers are going to disappear. And we just brought that pain forward, and the result was great. We hadn't explicitly told our engineers, hey, you have to write your services this way. Instead, we introduced this condition that drove high alignment among the engineers to automatically write their services such that they can withstand that kind of failure. It was very, very successful. And it's been years since any of our services, as far as we know, have had any ill consequences due to a server just disappearing. Chaos Monkey runs regularly. today it will turn off dozens of machines in our system. So we thought, okay, that's great. That's Chaos Monkey. Chaos Kong, now we also have this situation running in the cloud where an entire region will go down. So we thought, okay, let's take that pattern and apply it instead of just a server on the opposite end of the spectrum, let's apply it to an entire region. Let's turn off an entire region. Now, for whatever reason, I'm a little unclear about the details. Amazon won't allow us to turn off an entire region. Something about having other customers, yada, yada. So we simulate it as best we can, and we'll choose a region that's sick, and we'll move, the traffic team will move that traffic over to the other two regions. We'll slosh traffic around the globe, move it over to other regions so that we can fix the problem there, and then we'll move it back. That's Chaos Kong. And again, this has been very successful. It aligned all of our engineers without us explicitly going out and telling them how to run their services. It aligned them to build their microservices in such a way that they can run in any region, and they're always running in every region. And if one of those regions goes down, they can quickly scale up in the other regions, and our subscribers can continue to get the experience that they want. So we thought, okay, this is great. Chaos Monkey and Chaos Kong. There's something here. There's something here that's very valuable. So we sat down and we tried to figure out how do we formalize this into something that we can evangelize inside the company to help us get this better resiliency, which leads to better availability on a more regular basis, and also to other industries, because we like having peers. And so we came up with chaos engineering. And you can read about the formal definition there, but the one-liner is, chaos engineering is the discipline of experimenting on distributed systems in order to build confidence in the system's capability to withstand turbulent conditions in production. So we think of this as a new discipline within software engineering. And we know that bad stuff is going to happen in production because it just does. We live in a physical world. And so we want to empirically, we've got the word experimenting in there, we want to empirically bring that forward and help build confidence in the system by doing it in a controlled way. So I'll give you an example. So if we want to test the resiliency of service C, say that's the subscriber service that I've been talking about, we might take the cluster that's running on and spin up, or we're in the cloud, so it's easy to spin up new clusters. We'll spin up 2 new clusters that all get traffic from the same source. One's a control group and one's an experimental group. And we'll feed them live traffic. And we build a hypothesis, and the hypothesis is that our system is resilient to an outage in this particular service, or some sort of failure condition in this particular service. And then we apply that condition to the experimental group. It might be we don't let it reach downstream dependencies, or we introduce a bunch of latency, or something along those lines, something that could actually happen. And the degree to which the steady state behavior at the edge, the user's behavior at the edge, is the same for the requests that went through the control group as they are through the experimental group, is the degree to which we can add confidence to our hypothesis that we're resilient to that kind of effect. This has worked really well for us internally. I'm happy to say industry-wide, we've also gotten a really warm reception. Last year, we had a Chaos Community Day. This is from the poster from last year's, where we got fellow practitioners from Microsoft, Yahoo, Google, Facebook, the other companies that run things at scale. And we'll do this again at least once a year. So we're developing a community of practitioners, a community of peers. If you do chaos engineering, hit me up. We'll do this at least once a year. And we get to share all of these great stories about things that we've seen in production and ways in which we've gone ahead and simulated them and introduced them into our production systems, again, to build confidence in our systems by addressing these systemic effects. So while we were building that community, we also developed a gold standard above just an experimentation for additional principles that will help elevate us to the best level of chaos engineering. So one of those principles is build a hypothesis about steady state behavior. As engineers, we have a predilection to want to figure out how things work. And in this case, chaos engineering is more concerned with whether a system works, not how it works. So it helps us focus on what's really important, the business metrics or KPI or whatever you want to call it, by focusing on the steady state behavior of the system and building your hypothesis around that, and not trying to create a hypothesis about the internal workings. We're working on verification of the system, not validation of its internal model. Second principle is vary real-world effects. This is kind of a no-brainer, but we all have a lot of experience of things that happen in production. We want to recreate those things. Experiment in production. This is a little bit more controversial. Chaos engineering is not testing. If you're testing, you can write unit tests, integration tests, those sorts of things, and you can run those with synthetic traffic, and you can find lots of bugs, and you should do that. That's another great way to build confidence in your work. But this is an experiment, and there's no way, certainly at scale, to accurately duplicate your production environment. The experiment itself is going to have a systemic effect that could change your results. So we firmly believe that the only way to accurately build confidence in the system that you have now is to experiment on the system in production. Now, on top of that, for us, it's particularly infeasible for us to stand up a second Netflix as a testing environment, particularly when, for any of our hundreds of microservices, any of those teams can update any of those microservices at any point during the day. And a fourth principle, automate your experiments to run continuously. Any of you who are in operations, this is probably already obvious to you, doing something manually at first to figure out how to automate it, perfectly fine. But if we really want the confidence and a systemic effect to carry over, then you need to use it as a sort of a regression test. This needs to be running on the system 24/7. Particularly since the system itself could change at any time because anybody could update any of those microservices. So those are our four advanced principles of chaos engineering. So that's one story. That's my chaos engineering story about how we specifically use this practice to look at resiliency for those systems. We had another issue with systems, which is that because the engineering teams are experts on their own microservices, and because the system is so vast, there's no way for anybody to understand how all of those systems fit together. We don't have a chief architect at Netflix. A human couldn't even fit all of the pieces in his or her head, even if we did have a chief architect. So when my team is moving traffic from one region to another, sloshing around the globe, we need to know, are the regions that we're moving traffic to doing well? And because we're not experts in any of the particular microservices, we're certainly not experts in the holistic picture. So we needed a way to understand the service as a whole holistically. Essentially, if we have experts in these red microservices, that green layer of requests going between the microservices, nobody owns that. And because the microservices are coming and going so fast, there's no way for a human to own that. And chaos engineering gets us part of the way towards having confidence, regardless of not understanding that green spaghetti web. But we still want a better human way to interact with this. So we came up with what we call intuition engineering, and we have an application called Visceral that's our flagship example of intuition engineering. So what I'm going to describe doesn't have a formal definition yet. Maybe somebody here can help us come up with a formal definition of intuition engineering. But the point was, we've got this very complex distributed system, and we want to have a sense of its state. Now, we have great metric tools at Netflix, so I could put up dozens of charts and graphs of things changing in real time, but it's overwhelming. Human brain just can't parse information from that in an effective way. So we want a tool, some sort of interface that we can get that gut level feel of whether or not the system as a whole is doing well or something's a little bit off. I have an absurd metaphor, but it seems to work. One of the first things that we looked at is could we build a new sense for people around the state of the system? So imagine that we built a suit, and the suit is covered in electrodes. And the placement of the electrodes corresponds to the 400 or so microservices at Netflix. And when you're on call, you get the privilege of wearing the suit. We affectionately call it the pain suit. So you can imagine, you're at 3 a.m. in the morning, you wake up, my shoulder hurts, subscriber's down again. We hypothesize that after a very short period of time wearing the pain suit, you would get this extra sensory feeling for the state of the system, even when you wouldn't be able to explicitly say what the problem is. So if the system's different, you would just kind of feel it. And you might not even be able to put in words what that feeling is. But we've got great tools to do root cause analysis and to go delve into the network and figure out if things are wrong. So just wearing the suit would be enough to give you a feeling of, something's not right. So we haven't built the pain suit yet, but we built this visual analog that we call Visceral. So I'm going to show you the first screen of Visceral, if I can pop out of presentation mode here. I can't see the screen, so hopefully that's displaying. So what you see, ignore the numbers are irrelevant. The circle in the middle represents the internet, and the 3 circles in the corner represent the regions that we're deployed in. The dots moving between the internet and the regions correspond to volume of requests. The speed at which the dots are moving correspond to latency. The color corresponds to error code status, so blue is 200, reds are 500. There's oranges in there you might see every once in a while. And as long as I've been talking, while you're looking at this, your brain has already kind of sort of pretty much figured out what normal looks like for this time of day, given this traffic. In fact, it's so effective that we use this when we slosh traffic around. We have this up so that we can just at a glance look at it and go, yep, it looks good. And if the pattern of dots moving is different, we're taking advantage of the brain's ability to process vast amounts of visual data in parallel very quickly. We're taking advantage of that to just instantly form an intuition that, something's not right over there. The pattern of dots, you might not even be able to say they're moving slower or the color's off or something. The pattern of dots right there isn't quite right. So let's stop what we're doing and dig into that before we go ahead and move millions of customers over to that region. So this is the front screen of Visceral. We're going to open source this in about a month or 2. If you click on any of those regions, it will take you into this view, which is a view of the microservices within that region. So this is traffic coming from the internet in the upper left-hand corner, and then propagating through the very top layer of our microservices architecture. And I hid the labels because those aren't important. But again, from looking at this for a very short period of time, you just kind of get what normal looks like. And now if I run into a problem in production, I can bring this up and even kind of get an idea of something with those services up in the upper right-hand corner, something up there is not right. And then we have the tools to go like dig in and look at logs and do root cause analysis and all that to figure out what's going on in that region, or if it's nothing. So this helped us take a formerly intractable problem with this very complicated system and bring it forward in a way that we can develop an intuition of what, in this case, the system should look like. And that's been very powerful for us. I'll give you one more example of this. Here's that same first screen during a traffic failover. So you can see this is, again, for this time of day, this is what normal would look like. But in the upper left-hand corner, US West, the number of errors is starting to increase. And in this case, we sped up the simulation, so I don't know why the errors are there, but at some point the errors get high enough that we decide, you know what, we got to move that traffic over to US East. We got to move that traffic over to the other coast. So that bar along the top, what you see happening is our proxy layer in West is starting to proxy those requests over to the region in the East. At some point, as the region in the East scales up to handle that additional traffic, at some point it's ready to take all of it, so we go ahead and flip DNS. And then, it takes 5 minutes for DNS to finish, and then eventually all of the traffic that was going to US East is now going to was going to US West is now going to US East. And you can see that represented in the increased volume in the traffic going to US East. And we fixed whatever was wrong in US West, and then we reverse the process. We flip DNS back while we're still proxying over to US East so that we don't crush the region that we just fixed. And then we slowly taper back the proxying. And then we end up back in steady state. So again, feature velocity was one of the things we try to optimize for. And having this capability allows our engineers working on the microservices to really push the bounds of the features that they're implementing. And if, God forbid, something bad happens, we deploy regionally. So in that region, we can just evacuate the traffic from that region to the other regions, fix the problem, and then get back to the even spread that we want, and the service stays up. Most of the time, almost always, customers, the subscribers, don't notice when we do this. And that's what we want. So that's Visceral. Again, intuition engineering, we think of this as a new thing, and we're still kind of figuring it out, but we have some new interfaces that we're working on for Visceral and some other ideas for intuition engineering applications that, again, would give us an interface to a very complex system that gives us the capability of developing an intuition about the state of that system. Okay, and again, this is my simplified depiction of our microservice architecture in case there are any questions. And this is the awesome team I get to work with, so I just want to give them credit for it. That's my talk. I hope we have time for questions.
Thanks. Very nice
Cool.
talk. We do actually have at least 4 questions here. Cool. I want to remind everybody to vote, and then of course you can add some other questions as well. But the first one here is, how difficult is it to change the contract for one of the services when you have many consumers?
Yeah, so that depends on how quick-footed the consumers are, right? So I think it's actually provably the case that there's always a safe way, at least in theory, to update a contract while maintaining the old one. So at least we have that as a baseline, right? Whether or not we do that in practice is really up to the importance of that service. So do we always go that route? No. Sometimes we change stuff, and sometimes that means that other things will break because we change the contract between the microservices. But we have other programs that tell us how important microservices are for critical services like streaming video. So we have other tools that I didn't describe here, but I would love to talk about outside, that help us determine what are our tier 1 services? What are the services such that if any single one of them goes down, nobody can stream a video? And it turns out that's a small, very small subset, like 10-ish or so. And so for those, they're obviously going to be a lot more cautious about changing their contract, and anybody who they depend on is going to be more, going to keep that more front of mind.
Okay, thank you. This next question, which is one that I'm glad somebody asked because it's one I was thinking of as well. Has an experiment production ever gone so wrong that the downtime was substantially enough monetarily that management was unhappy with the situation at hand, like when you're playing Monkey Kong or whatever?
Yeah.
You know.
Monkey Kong. So I think there's two questions there. One, and I think the more fun one to think about is, have we ever gotten in trouble?
Right. That's basically.
So the VP.
Or cost money to the company or whatever.
Right. So that's a different. Whether we cost money is a different question, and whether we.
Yeah, I guess you could.
Whether we did a disservice to subscribers is a different question. So whether we ever got in trouble. So in my meetings with one of the most senior people that I report to, so a VP in the division that I'm in, he has told me that if we don't occasionally have surface a weakness in our system, then we're not pushing fast enough. And I think that's right. So we're very fortunate in that that at Netflix we happen to work in a place that understands the value of chaos engineering to the ultimate service that we're providing to subscribers, and so they give us a lot of rope to really push chaos engineering. So cost? No, we haven't affected cost. Subscriber impact. We don't like to negatively impact subscribers, of course. There have been times when experiments have negatively impacted subscribers, and in those cases, we have the functionality to turn those experiments off right away. And so we do that, and by the time they hit refresh, they don't realize that anything happened, usually.
Okay, thank you. This is a fun one. Have you ever tried releasing actual monkeys in the data center to see how services would respond to physical chaos?
So again, Amazon won't let us do these things. They won't give us the keys to the data center. But if I ever do get the keys, I'll keep that in mind.
Okay, how about this one? At Netflix, do you release code to production as soon as you identify chaos in production? And then it has a follow-up. If yes, how do you preserve the user experience while new code is pushed and systems are rebooted at such a large scale?
So everything. So we preserve the second part is easier to answer first. So we preserve the user experience by, if we identify a problem in a region, we deploy regionally in stages. So if we identify a problem, usually we're identifying it before that problem has propagated to other regions. So we could just turn that region off, move traffic to the other two regions while we fix it. Now, as far as how we handle a fix, ameliorate a problem.
But do you do it as soon as you identify chaos in production? That's the question.
Yeah. So no, because usually a chaos experiment is determining a potential vulnerability in the system. So what we do is we generate context for the service owners. Hey, you probably didn't think about this, but if your downstream dependencies go down, or if you switch over into serving things out of cache, then it could have this other bad effect on the user experience. So we're getting ahead of the problem actually manifesting in the system, which is really important. And then we give them the time to fix it in an appropriate way. And we don't watch that. They're the experts on their system, so it's up to them what their deployment pace looks like.
Makes sense. Okay. How are your SLAs affected by switching AZs?
So we don't switch AZs, we switch regions. By virtue of our business, we have this great advantage. Most websites have an SLA. They shoot for something like less than 600 millisecond response time, say. The great thing about working for Netflix is by the time somebody gets their popcorn ready and sits down on the couch and wants to watch their show, if that show takes, at worst case scenario, 10 seconds to start streaming, they're not getting off their couch. So the impact on our SLA of moving traffic to a different region is not noticeable to subscribers.
Okay. A couple more here. We have time for two. That's good. Does Netflix have synchronous or asynchronous microservices architecture? And then any observations on a particular approach?
Up until recently, the core pieces of Netflix's microservice architecture were synchronous, and that wasn't a problem. We're now moving several core components over to asynchronous communication IPC, and probably for reasons that most other companies wouldn't look at moving to async. Usually it's to alleviate our burden from internal service requests, not to handle increased traffic externally. So I can tell you, whoever asked the question, I can tell you more about that decision offline, but it's not the usual reason that you would go to an async system. We did put a lot of resources into looking at RX Java and RX Netty and reactive architectures, and those are very cool and advantageous in some conditions, but we don't see an impending need to move in that direction, because that would probably fall in the camp of over-architecting for performance at the expense of feature velocity.
Okay, and then we'll do one more, because then it'll probably break time, and then people can still, obviously you're around for the rest of the day.
Yes.
So do you currently use intuition engineering to predict failures, or is it more of a tool to address faster reaction times?
It's faster reaction times. So almost always. There have been cases where it helped us avert a disaster. For example, I had one engineer who had his finger over the button, enter, literally, and was about to move traffic from US West to US East, and he turned around and he saw Visceral up on the screen and yelled an expletive. And this was a very calm person, so everyone just froze, and he said, "Oh my God, okay, I was just about to move traffic over to this region, but I made that code change earlier today, and I forgot to put a gate that would prevent it from then redirecting to the third region. So had he hit enter, it would have brought the whole service down, because it would have sent the whole world to one region, and that wasn't scaled up to handle it. So it kind of prevented a disaster, but that disaster would have been self-inflicted."
Okay, let's thank Casey once again, and don't forget to vote.
Thank you.